Static electricity. So this is a real switch up from what we've been doing before in the mechanics unit. And as always, if you enjoyed this content, give us a like and subscribe. So to talk about electricity, the first thing that we have to understand are the details of the atom, because it's the atom and the particles in the atom that give us static electricity. So you know this from chemistry, but we need to review it just to make sure you know it. The center is called the nucleus, and in the nucleus we have protons, which are positively charged, and neutrons, which are neutral. I'm going to talk about the neutrons briefly, but they really have nothing to do with static electricity. Orbiting around the nucleus on the outside are our electrons. Electrons are negative, they're less massive, and they're easy to remove from the atom because they're on the outside, and they're also easy to add so that we can add or subtract electrons to change the electric charge of the atom. So let's look at more details of this. The proton is located in the nucleus, and sometimes the term for protons and neutrons are called nucleons. The mass of a proton, when we're talking about subatomic particles, is large, and you can look up the actual mass on the reference table. But for this unit, all we need to know is that compared to the electron, the mass is very large. The sign of a proton is positive, and the charge. Charge is the letter Q. This is very, very important. So it's usually lowercase q. Sometimes when we're talking about the net or total charge, an uppercase Q will be used. And there are two different units for charge. So we have charge measured in elementary charges, and we have charge measured in coulombs. This is C-O-U-L-O-M-B-S. I'll write it down. So, in elementary charges, this is 1. So the charge in elementary charges is +1 for a proton. In elementary charges, it is 1.6 times 10 to the minus 19th coulombs. On the reference table, all they tell you is one elementary charge is 1.6 times 10 to the minus 19th. So it's up to you to remember that a proton is 1 EC. And the symbol for a proton is P with a little positive sign. Now, neutrons are also located in the nucleus. They are also large in comparison to the electron. Their sign is 0. They have no charge, and the symbol is an N with a little 0. Now, that's it. We're not going to talk about neutrons again because they have no electric charge, so they play no role in static electricity. The electrons are in orbit about the nucleus, so they're on the outside, which makes them easy to add and easy to remove. The electron is small, much smaller than a proton. And when we're talking about mass, this is going to come into play when we talk about acceleration. A proton is harder to accelerate in an electric field because of its large mass. An electron is easier to accelerate in an electric field because of its small mass. The electron sign is negative, and these need to be memorized. And the charge is also 1 EC. So even though a proton is much larger in mass, that means the gravitational field affects it more, the charge is exactly the same. So if we put a proton and an electron in an electric field, then the proton and electron will feel the same amount of force on it because the charge is the same. So therefore, if this is +1 and this is -1, then the charge in coulombs must be the same, 1.6 times 10 to the minus 19th coulombs. And the symbol for an electron is E with a little negative sign. Let's solve a couple of problems. Let's say that we have 5 electrons, and we want to know the charge of that in coulombs. So what we do is we take the 5, That's e to the negative, and all we do is multiply it by 1.6 times 10 to the minus 19th coulombs. Why? Because that's 1.6 times 10 to the minus 19th coulombs per electron. So electrons will cancel, and we'll be left with 8 times 10 to the minus 19th coulombs. Now, it's electrons, so we need to add a negative sign. When you do this on your calculator, I highly recommend doing it with the exponent key. So that's 1.6, then do your second exponent key, so that's second, double E, and then your negative sign, and then your 19, and then multiply all of that by 5. And that gives us our answer of 8, and they even give you a little times 10 to the minus 19th. So here's a different question. How many protons do we have in 1.28 times 10 to the minus 18th coulombs? So they've given us some charge, that's our charge Q, and they want to know how many protons that is. Well, if we take that number and we say that one proton has a charge of 1.6 times 10 to the minus 19th coulombs, then by dividing this number, coulombs will be canceled and we'll be left with protons. So we do the same thing, which is our 1.28 second exponent, negative 18, and then we're going to divide that by 1.6 second exponent key, negative 19, and that gives us 8. So the answer is 8 protons. Now, sometimes this question is asked a different way. It's asked as, what is the excess charge? So here's an example of this where we want to find the excess, and excess means extra or leftover. So we have 3 protons, and 1, 2, 3, 4, 5, 6, 7. We have 7 electrons. So we have negative 7 ECs, and we have plus 3 ECs. So what are we left with? We're left with negative 4 ECs. That's our excess. So how do we do this? The same way we did this before, which is going to be 4 electrons. And we know that we have 1.6 times 10 to the minus 19th coulombs for 1 electron. So we multiply through, our electrons will cancel, we'll be left with coulombs, and that gives us 6.4 times 10 to the minus 19th coulombs. What makes something neutral? So why would an object be neutral? Most objects are neutral, and the reason that objects are neutral is because they have equal amounts of positives and negatives. In this case, protons and electrons. So let's say we have a balloon, and in this balloon we can count up our protons, 1, 2, 3, 4, 5. We count up our electrons, 1, 2, 3, 4, 5, and we have equal amounts, so therefore the object is considered neutral. Now, a balloon is a really good example because it's made of rubber, and when you rub a balloon on hair, for example, you end up getting a transfer of electrons. Now, typically with a balloon ends up holding on to its electrons because it acts more like an insulator. So in general, when you rub a balloon with hair, you end up getting more electrons transferred from the hair onto the balloon. So in that case, the balloon becomes charged. So when an atom or when an object is unbalanced, in other words, it has a net charge, then we call this electrically charged. That's the definition of electrically charged, is when we have an unbalanced amount of protons and electrons. But let's get rid of these 3 and make it go back to neutral. Is there a way that we could make this object positive? We added electrons, which gave it a net negative charge, but what if we remove electrons? In that case now, it's an unbalanced amount, so it's electrically charged, and it has more protons than electrons. Therefore, this balloon would be positive. What is an electric field? So before we talk about an electric field, let's just talk about fields in general. So a field defines the shape governed by the direction of the force on a particle. And we can have many different types of fields. We can have gravitational fields, we can have electric fields, we can have magnetic fields. But in the case of gravitational fields, it's the force on a mass. Whereas with electric fields, it's the force on a charge. So for a mass, we only have one type of mass. There's no such thing as positive mass or negative mass. So what's the shape of the gravitational field around a large mass? Well, what we do is we look at the direction of the force of a small test mass. So we have something called a test mass. It's neither positive nor negative. And we place this small test mass in the field. So here's a mass, a large mass. It creates a gravitational field around it, and the direction of the gravitational field is the direction of the force on this small test mass. So if we place this small test mass here, it's going to be attracted to this larger mass, and the direction of that force is the direction of the gravitational field. And if we put it here, it's going to go in that direction, here, and here, and here, and so on. So it's going to be attractive only. So gravitational fields only attract. And the force that's acting on the mass is going to increase as it gets closer, and we'll see a formula that actually tells you why that is. But I think that's rather intuitive and sort of makes sense with what you would expect, that as you get closer, the force would get larger. Well, what happens if we have a much larger mass and therefore a much stronger gravitational field? Well, the way that we draw that is with more lines. So the concentration of lines, the line concentration, which is called flux, tells us how strong the field is. So here we can see that the lines are closer together, so this mass would have a much greater force on it. Also notice this. Sometimes they ask you this question. They'll ask you to identify a region. In here, there's lots of lines. If we go further away, the same amount of area contains less lines here, so the gravitational field is weaker at this location compared to this. So now that we understand how a gravitational field works, now we can talk about how an electric field works. So an electric field works pretty much the same way. It's the shape of the field created by the force, but this time, listen carefully, it's the force on a positive test charge. So when we dealt with mass, there was no plus, there was no minus. So mass always attracts towards other masses. But when we define an electric field, it only depends on what the force is on a positive test charge. It has to be small because we don't want the thing that's measuring the field to disrupt the field itself. Now, when we do this, you don't get a choice. The positive is defined in physics as the direction of the electric field. So let's go ahead and look at an example of a large positive charge. What we do is we take the positive test charge, so here's our small positive test charge, and we place it in the field. Well, what's that going to do if it's near a large positive charge? Well, plus and plus, like charges repel, so it's going to move like that. What if we put it here? Well, it's going to move out this way, and here, and so on. So that it's going to act radially outward, so that the shape of our electric field looks like this. Now, there's another important part about electric fields, which is that field lines never cross. They never cross each other. They can become asymptotically closer to each other, but they never cross. Okay, let's look at a large negative charge. It's a negative charge, but we still use the positive test charge. If we put this in the electric field, this time it's going to attract. From here it's going to attract, 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 and so on, so that the shape of the electric field is going to be the same as around the positive charge, except this time the arrowheads are pointing in. Here's the shape of the electric field around a large positive charge and a large negative charge that are located near each other. Now, we know that these two charges would end up attracting to each other. But what we're saying here is that these are fixed in place. So we just have you could think of it as glued in place, this large positive charge, this negative charge is glued in place. And then if we take our small positive test charge and put it anywhere in this field, the direction that it travels is the direction of the electric field. So if we put it here, it's going to repel from the positive and attract to the negative. So the direction of the electric field is directly from left to right. But think about it here. Its initial repulsion is straight up, but it's simultaneously being attracted to the negative. So it starts to curve. And as it gets further and further away from the positive, the force weakens. So this force is getting weaker and weaker and weaker. And then it starts to get closer to the negative, so the force starts to increase on the other side. So we have this shape of this field determined by the shape of the direction of the force on this small positive test charge. What does it look like if we have two large positive charges? Well, in this case, if we take a point right here, this is going to repel from the positive with a great deal of force because it's close. But it can't go straight away, because if it did this, it would be getting closer to this positive. So it's repelled mostly by this, but a little bit by that, and so it ends up moving away. Notice that if we look at the other side, that these lines can get closer together, they can never touch, they can never cross. And the same thing happens down on the bottom. If we're on this side, we're only repelling, so it's straight. From here, it's repelling. It wants to go straight up from this one, but there's an additional vector force that way, pushing it out in this direction. How does this field differ when we have two large negative charges? Well, if you think about it, from the picture we just saw, the shape is exactly the same. But the difference is now this small positive test charge is feeling a force of attraction. So it ends up moving in, and so on, so that it's the same shape, but with the arrowheads pointing in the opposite direction. When we have two metal plates that are close to each other, and one's charged positive and the other's charged negative, this is called a capacitor. Now, this course doesn't get into capacitors, but you still need to know the shape of the electric field. So if we put a proton here, it moves directly across to the negative plate. So this produces a uniform field. We'll see this in a moment, that the field has an equal amount of strength here as it does in the center, as it does on the other side. At the edges or fringes, there's a little bit of curvature that happens because there isn't a force to balance out and cancel the vectors that we see in the center of the capacitor. So let's look more closely at the capacitor. Here's a common question. If we have a test charge, could be a test charge, could be a minus, could be any charge that we put in between these fields, we're going to feel a force. Now, I'm going to do this for a positive charge. That means that the field is to the right, but I'm just going to point out that we could also do this for a minus. This would not be the direction of the field. This would just be the force on a negative. The negative moves opposite the direction of the field. So a positive placed in an electric field points in the direction of an electric field. A minus will feel a force opposite the direction of the electric field. So this arrow that I'm drawing right here, that is the direction of the electric field. It's also the direction of the force on a positive charge, and it's opposite the direction of the force on a negative charge. But how does this force differ in these different locations? When we're close to the positive, when we're in the center, and when we're close to the negative? Well, when we're located close to the positive plate, the force from the positive on the positive, it's very close, so the force is large. We'll make up some numbers and say 3 newtons. But this positive is also attracted to the negative plate, but because it's far away, the force is small. So both forces acting on this small positive charge are to the right, and the sum of the force of 3 plus 1 is 4. If we put it in the center, then the force on this positive charge is medium because it's sort of in the middle here, so maybe we get about 2 newtons, and the force of attraction between the plus and the minus plate is also medium, so we get a force of about 2 newtons, and again the force total is 4 newtons. And finally, if we put it on the negative plate, the force of attraction due to the positive and the negative plate is large, and the force of repulsion between the plus and plus is small, again giving us 4 newtons. So what do you need to remember for this? You need to remember that the force on a charged particle between two electric plates, the electric field is uniform and has the same amount of strength at any point between them. So let's say we have a capacitor and it's oriented in this plane in this direction. We know that the electric field would be down in this case. But that doesn't mean that we can't project a negative charge into this field. So let's say we have a electron or a negatively charged particle, and it goes flying into this electric field with a high velocity. Well, when it gets into the field, it's going to be attracted to the positive, and it's going to be repelled by the negative, and those directions are both up. So what's going to happen if we have a force up with a velocity in this direction? Well, that's going to make it curve, and that curve is going to be a parabola. This is basically an upside down kinematics problem where we have a projectile launched off of a cliff and it makes a two-dimensional curve, a two-dimensional parabolic curve. In the problems with gravity, of course, it went down in that case. If we project the electron at a great enough speed, we can end up getting it to completely leave the plates, even though it will still curve. But what happens if we have a particle in an electric field? And again, we'll put a minus in here. The electric field is the direction of the force on a positive charge, so that's down. But what is the electron, or in this case, a small negative charge, what's that going to feel? Well, we know that the electron is going to be attracted to the positive and repelled from the negative. So it's going to experience a force up that we can call force E, the force due to the electric field. Well, what if that force is exactly the same as the force due to gravity? Well, if that's the situation, this electron will just levitate. If the electric field is larger than the force of gravity, it will accelerate up. And if the force of gravity is larger than the electric field, it will accelerate down. Well, let's look at one more situation, and that is the situation where we will put a negative charge over on this side, and we will put a positive charge over on this side. We know that the electric field is the same all the way through here, but the masses of these particles are different. Also, the charges are the same. So if the electric field is the same and the charge is the same, the force due to the electric field is equal on both particles. So which one will have the greater acceleration? We know the plus will accelerate over here, and the minus will accelerate over here. But which one will have the greater acceleration? The one that has the lower mass. Remember, electrons have a lighter, they have a lower mass, so that will accelerate more quickly than the positive, the proton. This is probably completely obvious, but I need to say it anyway because it is important. What happens when we have a positive and negative that are free to move? Well, opposites attract. So, like I said, you probably know that. But what's going to happen? This question has come up on physics tests before on the Regents exam, which is what happens to the strength of the force acting on the particles as they accelerate towards each other. Well, first of all, the force is equal. The positive pulls on the negative as much as the negative pulls on the positive. Why? For every force, there's an equal and opposite force. That's Newton's third law. Now, they're not going to meet in the middle because the electron has less mass than the proton. So they're going to accelerate and meet somewhere over here on this side. But what's the thing that you need to remember? That the forces on these are going to increase as the distance decreases. What happens if we have two protons? Well, in this case, the force is going to decrease because they're going to repel, and as they move further and further away, the distance increases, so the force decreases. Almost all of the questions in static electricity in some way involve this concept of objects becoming charged through friction. So the removal or addition of electrons is the result of friction. So when you have two objects rub against each other, electrons get rubbed off or electrons get added. Now, this may seem strange because in the nucleus we have all of these positives. Shouldn't they be repelling? Well, they're not repelling because there's an additional force acting on protons that holds them together. This is called the nuclear strong force. We'll get into that in the modern physics unit. All you need to know for now is that the protons are pretty much locked in place. They're stuck inside the nucleus and they can't move outside of the nucleus. So they're stuck inside the house, sort of. Whereas these electrons are in orbit around. This atom would be electrically neutral because we have 5 electrons and 5 protons. But if we have some friction, we can actually pull off some of these electrons from rubbing. So the rubbing pulls or strips off the electrons, making it, in this case, a positive atom. We can also take a neutral atom, rub it against an object, and add electrons. By adding electrons, we end up making the object electrically negative. So, objects become negative by gaining electrons, and they become positive by losing electrons, and this process occurs from friction. So this is a common question that comes up, and basically what they're going to ask you is if the fur rubs up against the rubber rod and they say, let's say for example, they'll say that the rubber rod becomes negative, they'll ask you how it became negative. Now, it turns out that rubber rods are very good at holding on to their electrons, and fur or hair is very good at losing electrons. But you don't need to memorize that because they're going to tell you which one loses the electrons or which one gains. So let's say that we rub the rubber rod against the fur and the rubber rod becomes negative. Well, the question would be, why does it become negative? And the answer is that it becomes negative because it gained electrons. So the only way that an object can become negative is by getting more electrons, and the only way that an object can become positive is by losing electrons. So the fur becomes positive from losing electrons, and the rubber rod becomes negative by gaining electrons. But there is something called the law of conservation of charge, which says that the net charge must remain the same. So although this is positive and this is negative, the total charge of the system has to be equal to the charge that we started with. Well, what did we start with? Two neutral objects. So the net charge of the system is 0, even though this is negative and this is positive. Now it turns out the opposite happens when we have silk and a glass tube. In this case, glass tubes are very good at losing their electrons, whereas silk is very good at holding on to them. So if we rub the glass tube onto the silk, the question might be, well, why does the glass tube become positive? Well, in this case, electrons would be transferred to the silk during the rubbing, which is the result of friction. So we end up doing that, and the silk becomes negative because of a gain of electrons, and the glass tube becomes positive because of a loss of electrons.